Hello, today we're going to talk about weight-free data structures and weight-free transactions and how the two mix. Hopefully, if there's some time, we'll talk a little bit about how that goes into key value stores. So my name is Pedro and I've been working for 10 years in concurrent stuff. That means Readerwriter locks, mutual exclusion locks, universal constructions, Lockfree data structures, this kind of stuff. And for these past 10 years, I've been doing that with Andrea, which you see down there in the photo. And like 3 years ago, we started collaborating also with Pascal Felber. So during this presentation, if I say we, that means these guys as well. It's not just me. And right now, I work in Cisco Systems writing software that scales, and occasionally I write some blog posts at Concurrency Freaks. I don't know if anybody has ever heard of that or not. So anything I'm going to say here, some parts of it are facts, but mostly it's my opinion, so it's worth what it's worth, and any errors, they're just my own. They have no reflection on the people that I work with or the company that I work with, and should not be used to decide purchasing decisions. So I want to start with concurrent data structures, but before we go there, I'm going to have to talk about the basics. And some of you will be bored because you've heard of all of this already, and others will not, so that's how it works. So the first thing is, what is lock-free and wait-free and blocking? And blocking, pretty much everybody knows what it is. It's, well, when one thread has to wait for other threads. And this is what a mutex does, or a reader-writer lock. And then you have things that are non-blocking, and the simplest or lowest of that is obstruction-free. And since I only know of one data structure that is obstruction-free, I'm not even going to talk about it, because you can look it up if you want. The most famous of all is certainly Lockfree. Now, Lockfree, what it does, it guarantees you that one thread calling a method will eventually finish, and it's going to finish in a finite number of steps. With the probability very close to 1 at least. Now, this has implications, and one of the first implications is that if n-1 threads or processes die during operations, the one that's left alive can still make progress. It can still do its work. If this is not true, then that algorithm is really not lock-free at all. It also has another implication, which is, well, we're guaranteeing that one thread or one process is going to complete its work, which means all the others might never complete its work. So lock freedom implies the possibility of having starvation. So in starvation, when you look at it from a latency point of view, at the latency distribution, it means that some threads may be executing and never complete their work, so you get a fat tail in the latency distribution, for those of you interested in this stuff. Then the next step after that, with more guarantees, is wait-free. Now, wait-free, everything that is wait-free is also lock-free by definition. And wait-free guarantees that all the threads finish in a finite number of steps. Now, this one changes from lock-free in the sense that now you do have some guarantee that not only is it fair, because you know that all the threads can execute their work, but you also have a guarantee in the tail latency. Typically, that's not true for all wait-free algorithms in practice, but you know that there will be some place where the tail ends. Now, the tail of the distribution ends. Now, that tail end might be so long and takes so long that in practice it doesn't really matter. So it looks like a starvation algorithm, but it gives you this possibility. And inside the wait freedom, you have the wait freedom bounded, which means you know how to compute what is the number of steps that the algorithm is going to take. So there's a formula, let's say, to compute that. And even more than that, you have wait-free population oblivious, which means you have a formula to compute, and that formula does not include the number of threads. So that means tail latency should not be affected by how many threads are competing to do that operation. During the presentation, I'll talk about a data structure being lock-free or a data structure being weight-free. So when I say that the data structure is lock-free, it means that all of the methods have to be lock-free or weight-free, one of the variants of that. And when I say that the data structure is weight-free, it means that all the methods have to be weight-free. And of course, then there's the whole thing of what about memory reclamation? And so maybe my opinion isn't the same as everyone, but I kind of think that, well, at least in most of the cases, to be truly lock-free, you should have a lock-free memory reclamation scheme, and to be weight-free, you should have a weight-free memory reclamation scheme. And there are even more radicals than me that say, well, if it does allocation and deallocation, then the allocator should also be weight-free, and deallocation should be weight-free. So let's not go into that, but just to say that these are factors that influence depending on the context and depending on who you talk to. So when I talk about blocking, I'm talking about locks, reader-writer locks, concurrent hash map in Java is blocking. And when I talk about lock-free, I'm talking about the Meg-Michael and Michael Scott's queue algorithm, which is implemented in Java as concurrent link queue. I'm talking about the linked list set by Meg-Michael and Tim Harris, these kinds of things. And when I talk about weight-free, I'm talking about the Kogan-Petron queue or the sim queue or the turn queue. And the thing about blocking is, unless you have some other mechanism on top of it, it will not be resilient to failures. And typically, it also does not have deterministic tail latency. So what that means, so there is an exception to this, which is when it's starvation-free and there's no oversubscription and a lot of other conditions. But let's say typically that's not how it happens. For lock-free, again, we have the resilience to failures. We just don't have really the guarantee of a tail latency cutoff. And, that's how it is. And for weight-free, we have the guarantee. Again, it's a theoretical guarantee. It doesn't mean in practice it really happens. For tail latency. And the thing to look at it here is that I didn't mention throughput or scalability anywhere. So lock freedom and weight freedom aren't about throughput or scalability. For me, they're about these things. And in fact, most lock-free algorithms have a high cost in synchronization, so that means they can even run slower on a single-threaded execution than a blocking one. That's usually what it happens. So again, just to consolidate the idea, if you have 3 threads accessing a resource, and one of them takes the lock, and then dies after acquiring this lock, the others will not be able to access the resource because it's blocking, it's a lock, it's blocking. There's no other way, and they'll spin forever or die waiting. And if it's lock-free, then if one thread dies while accessing the resource, well, if it's lock-free, it means the others can still do their progress and do whatever they need to do because the algorithm for accessing that is lock-free. So that's what it means. Another thing that's in the basics is consistency models. Now, I'm going to focus on linearizability because linearizability is what a mutual exclusion lock gives you. And everybody knows how to reason about locks. Locks are very intuitive because they work in a way very similar to the real physical world. And so even I would say even a developer fresh out of college would be able to use locks correctly in most situations, or at least if it's just 1 or 2. And there are a lot of consistency models, and none of them is right or wrong, although linearizability is way easier to prove correctness in academic proofs. But none of them are wrong. It's just a matter that we focus about that because linearizability is very easy compared to the other ones below them. It's very easy to reason about for us humans. And what happens is if we go for a very relaxed model, it's going, let's say I write a data structure and I give it to a developer for usage and it's a black box. That developer is going to be surprised by some of the behaviors unless it is linearizable. And because of that, he's going to say, your data structure is buggy. Anything below linearizability is buggy. And he's not right, or he's right, and I'm also right. I can make a correct weak data structure, but it's just who's wrong here? There's no right or wrong. It's just the way, it's just an API kind of approach. What do the users of the data structure expect? And I would argue that most of them expect linearizability because that's the easiest to reason about. One more definition, which is called disjoint access parallel, is used a lot in the academia, not so much in the industry. And basically what it says is that a certain workload is disjoint access parallel if all the modifications are occurring in different places, in different pieces of data. And read-only modifications, read-only operations do no modification, so by definition they're disjoint, so they're DAP, let's call them like this. And DAP is a property of the workload, okay? So it's related to the interaction between the certain threads and what operations they are doing. But we can also squeeze a bit this definition and say, well, there are some data structures that they kind of imply that you're going to modify always the same thing, so they're non-DAP by definition. Let's see an example. Suppose I have a stack, and the stack has a node there. Oh, sorry, wrong one. That's okay, you can see that. So there's a head pointer, and then there are two nodes, and all of these three threads, they want to push a node into the stack. Now, because of this, they all want to modify the head pointer, and of course, they cannot do it all at one time, so this stack is not DAP. It cannot be disjoint, and it's something related to at least this particular implementation of a stack. So this particular implementation of stack is not DAP. No workload you can put on top of it will be DAP. Then you have other things which are naturally DAP. Doesn't mean the workload itself will be, but and the example, the simplest one, is a hash map where on average, you expect if the keys are properly spread, they'll end up on different buckets, so they won't touch what each other are doing. So that's kind of a DAP work, a data structure. A few other terminology that I'm going to use through this presentation is a sequential data structure. So a sequential data structure is a data structure that's been written for single-threaded. It's just something, if you want to make concurrent, you have to wrap it with a lock, for example. And I'm going to talk about CAS, and CAS is a compare and swap. On C, C++, it's called compare and exchange strong, typically. In Java, it's compare and set. So it atomically modifies a word if it has the expected value, changes it to a new value. And then there's DCAS, which is a double word compare and swap, which modifies two words adjacent in memory, right? It modifies them at the same time. Doesn't exist on Java. Maybe one day it will, who knows? Okay, so that was the introduction. How about Clockfree data structures? You know, they can't be that hard, right? Well, let's say you have a sequential data structure. So it's written for single-threaded code. Even a developer fresh out of college can reason about that, and they can just put a global lock on that, and now you have a concurrent data structure. It's very easy to modify that and get that concurrent data structure. If you want to use fine-grained locking, then you have to go into hand-over-hand locks, and it takes a little bit more time. You have to have a bit more experience, study the problem a bit harder. So it takes a bit more of a senior engineer. And then there's like this gap, which is almost an abyss, where you go from that to designing lock-free data structures and wait-free data structures. And it takes someone like Maurice or Michael Scott or Panagiotta Fataru, Erez Petran, Cliff Click, you know, all these guys, they've studied years to understand what the memory model is and atomics, and it's really a lot of hard work to get to that, to the other side. And is it worth it? You know, like, can the common developer afford to invest all that time when we already have to learn about like how the compiler works and the multiple languages, because usually it's not just one. You have to do tests in one language and develop in another, and you have to understand the compiler and the JIT and hardware and cache lines and CPUs. I don't know. The list goes on. And on top of that, we have to understand concurrency and design lock-free data structures. I mean, that seems a bit too unrealistic. So, what if we have a queue, a singly linked list queue, and we want to protect it with the lock? Now, who here would feel comfortable designing such a queue. So it's just a single linked list queue, and you protect it with a global log. Okay, so a big fraction, given enough time, like a couple of hours. So I did this one. I hope it doesn't have any errors. And it's in C++, but you can see that it's just a matter of grabbing a lock for the enqueue and grabbing a lock for the dequeue. It's 12 lines of code. And if I want to change this queue to do something extra, it should be fairly easy. If I want to traverse the queue or now turn it into a doubly linked list queue, so I can insert also on the other side, it should be easy to do. What if it's lock-free? Well, if it's lock-free, the code is a bit larger, so you get enqueue there and dequeue there. It's still small, it's still 23 lines of code in this particular implementation, and it even has asset pointers to protect memory reclamation and all. But, I would challenge the majority to change 2 lines here and not break this algorithm, even if it's just to refactor. So it takes a couple of hours to put this algorithm in your head, go through it, what it really means, all the nuances. It's not easy. And this is, apart from Triber stack, this is the simplest lock-free data structure there is, likely. Okay, so it's very simple. What if it's a wait-free queue? Well, that's the enqueue, that's the second part of the enqueue, that's the first part of the dequeue, and that's the second part of the dequeue. And you have to imagine all the possible interleavings of all these lines of code with each other. And there's about 80, so I don't know how 80 to the power of something goes. But it's hard, and it's very hard to modify it. It's very hard to adjust it to do something else besides what it was originally intended to. And it's even hard just to read it and understand what it's doing now. So even the experts have difficulties with lock-free data structures. So obviously, we're gonna have difficulties as well. Creating a new lock-free data structure can take months of work by an expert, and customizing it could take, again, weeks or months of work. And even if you have the skills, or if you can afford to hire someone who has the skills, what about when they leave and then you need to change it again to suit some particular business need, because my experience with data structures is, yeah, sometimes they're used just as black box containers, and that's fine, but most of the times software engineers want to change it and tweak it and make it their own and make it do something else that it wasn't intended to do. And then you should try to get a correctness proof, and proofs can themselves have errors. We're humans, we make errors, that's normal. And then there's the whole memory reclamation thing, which almost nobody adds memory reclamation to their lock-free data structures. I think I've only seen one data structure with this, so that's how that goes. But what if there was this magical device that we could take a sequential data structure and transform it into a data structure that is concurrent and safe, and even has wait-free progress? Well, there is such a thing. It's called software transactional memory and universal construction. So both of these things can give this magical property. So let's go back in time to 1991, when Maurice Early introduced the concept of the universal construction. And the thing is, he didn't just introduce this concept, he actually showed an algorithm that implemented this, and it actually worked. So, okay, it wasn't all that fast. Back then, there were no copy constructors, maybe, and there was no memory model or all the other stuff that, meanwhile, has been discovered. So it was kind of hard to use. It was more of a recipe on how to transform the sequential data structure. But you can take that algorithm today and implement it into something that does it almost magically. So it does work. And it was the first time that it was possible to make a wait-free data structure without having an expert by your side to do it or hiring one. So pretty much anybody could do that. For me, that's really amazing. The thing about universal construction is that it provides wait-free progress, but it's for a single data structure. You protect a single object. What if you want to do operations over multiple objects, but you still want them to be wait-free? Well, 2 years later, again, Maurice and J. Elliott Moss they got together and they introduced the concept of a transactional memory. Now, if you can see the title of their paper, it's something to support lock-free data structures. So it really was their intent, at least from the title, to make it such that it was easier to design and implement lock-free data structures. The thing is, it was made for hardware, and the hardware folks didn't pick it up for many years. And so a couple of years later, Nir Shavit and then Toy2 presented the first software-only transactional memory. So they made an algorithm that actually implemented this concept. Was it Lockfree? I don't even remember. And during the decade of the 2000 to 2010, there was like a deluge of STMs. Everybody had STMs, and they do, at least on the academia, and they used it for lots of papers on that. There weren't that many that were lock-free, or attempted to be lock-free, but there were some. And then 3 years ago, me, Andrea, Pascal, and Nachshon Cohen, we got together and we made what I think is the first weight-free software transactional memory, and it got published 3 weeks ago at DSN. Now, the thing about one file, it's called one file because everything is in one C++ header, so it's not that big, it's just 1,000 lines of code, okay? And you just include this header and compile it with your compilation unit, and you're ready to go. The bad side is it serializes all mutative transactions. So we'll see later what this means, but basically it doesn't scale for writes very much. And it needs this decas instruction. It's possible to work around that, but it has other limitations. The cool thing, it has weight-free memory reclamation, and it's pretty efficient at doing so, and it even works on persistent memory. And actually, it can also do weight-free allocation and weight-free deallocation. So with this kind of stuff, and I'm sure others will come after this. This is just the first of many STMs, I hope. And with this kind of stuff, you can take the sequential data structure, you do some modifications, some annotation, and you get a weight-free data structure. Now, what do I mean by annotate? Well, we have to do a lot of tasks. Let's look at an example because it will be easier. So here we have a sequential linked list queue. You have a node there, a head and tail pointer. We have the enqueue function here and the dequeue function there. And the first step is just to include the header. So that's kind of a silly step, but it's there. You need to do it. The second step is to annotate all the variables, all the types that are going to be shared among multiple threads. So that means the next pointer of each node, and that means the head and tail pointers of the queue. And then the next step is to, you have to extend, make all objects that you allocate and deallocate dynamically extend from a thing we call TM base, so something in the STM. So that means the nodes of the data structure and even the data structure itself, because you might want to allocate multiple during a transaction. And after that, you put everything in a lambda and pass it to this function that's called an update transaction, so a mutative transaction. And here is the same thing. This is the semantics for calling a lambda in C++. And this means everything has to be captured by copy. And the last step is to replace the calls to the allocation, so new and delete, with our own tm new and tm delete, so that we can do the weight-free memory tracking. Now, this is a lot of clutter, let's say, as it is today, but the thing is, all this code is still sequential. Inside this lambda, this is still the same code it was before. I can reason about it. It's still sequential. Same thing here. And as technology progresses and as compilers and other things go on, we can replace almost everything, maybe even everything here, with something that the compiler does for us. So all of this clutter will eventually disappear if people find use in this, of course. So what makes a weight-free STM? Well, one of the main components is the multi-word cas. This is a thing that allows you to modify multiple locations in memory atomically. We have a slightly new one that has no bit stealing. It's nothing special, but it does need the double word cas to work. Then we have a redo log where all modifications are kept. And we use that for both the concurrency and the durability. Again, this idea is not new. It's been done before. And then we use a consensus because all weight-free algorithms need a consensus, and we use the one by Maurice. And we use a memory reclamation called hazard errors, which is pretty efficient for this kind of stuff. And here we modified some stuff and to get it to be weight-free. And there's some innovation there, but again, it's not something major. So this is the part where I'm going to go over a bit over the Lockfree algorithm. So if you find that kind of stuff boring now, you can check your emails and I'll let you know when it's over. So we start by, it has 3 steps, and the first one is called transform. So we transform our lambda into a log, a write set that contains all the modifications that are being done by that particular transaction. And that, so it takes the lambda, puts it in a stud function and does that. And then it just does one cast, a single cast, to commit the transaction. So to decide who is the thread that's going to submit its operation. And then the next step is simply to take the redo log and apply all the modifications using double word cast. So let's see how this applies to a stack. If you want to protect a sequential stack with the one file algorithm. You have the current transaction variable, which holds a sequence and the thread ID. And then you have the request, which is not needed for correctness, but it has to match. And then you have a redo log, which is called the write set on STM terminology. You have this redo log, 1 per thread. And there, we're going to log all the addresses and values of the things that we want to modify. So let's say the stack as it is already there, there's a head pointer which uses sequence 4 and the pointer to a node. And inside this node, there's a key and a next. The key has sequence 4 again and the value of 33. And it has a sequence 4 and the next is just a null pointer. And let's say we have 3 threads doing each their own operation. So thread 0 wants to do a push, this one wants to do a pop, and that one also wants to do a push. And what they're going to do is they're going to, again, take their lambdas and simulate them and save all the stores into their own redo logs. So as you can see, the only modification here is just at the location of the variable head, you change it to next. So which one is this? It's there. So at the location of head, you change it to next. That's what it means. And once they have that, they're going to try to change the current transaction to point to its own redo log. So they're going to try to change this 0 here to whatever that thread ID is. And in this case, it was thread 2.1, so it changed it. It incremented the sequence, so there are no ABA problems. And then it says, okay, the next transaction to be applied is going to be mine. So that means everybody has to apply this redo log. So what the other threads do now, once they see that the transaction has changed, is they go and they make a copy of the redo log of thread 2, and they put it in their own redo logs. So it's the same thing there. So now everybody has the same one. And now they all can apply, what happened here? Okay. And now they start to apply one decas at a time. And this part is kind of interesting because what this means is that because there are multiple entries in the log, each thread can do its own decas. So there's some parallelization here, but which in some cases allows some scalability. So again, this, and then you got the new node, and once this thread is over, everybody changes the request to match, and that completes the transaction. And now that job is done. So you still have T0 and T1 which have not done their work. And again, remember that part is lock-free, so it could, some other thread can come in and keep on jumping in front of them and doing their work, doing its own work and not letting T0 or T1 progress. So lock-free implies possibility of starvation. For the read-only transactions, we used a technique which already existed for a long time. We took it from TL2 and TinySTM. It's pretty much the same with the minor tweaks. If you're familiar with databases, it's kind of optimistic concurrency control. So TL2 uses, for the write transactions, something like two-phase locking, very similar to two-phase locking. And then for reads, uses this optimistic concurrency control. And for the reads, we do that as well. Now you may be wondering, well, what about hardware transactional memory? How does that fit into that? Well, hardware transactional memory as it stands today in all the current implementations does not give you any guarantee of progress. So whenever there are conflicts, they're going to abort and retry. And then they're going to retry again, and they're going to retry and retry. And there's no guarantee that they will ever succeed. Any thread will ever succeed. They may be stuck doing something very simple for all eternity. So that's not lock-free. It's blocking with the possibility of starvation. So as it stands today, hardware transactional memory cannot give you lock-free guarantees. Perhaps one day it will, I hope so, because that would make things better. So we looked at the lock-free algorithm. So now but we're gonna end with algorithms. So if you can now stop watching your emails or something. And now we're going to look at waitfree. Now, one thing about waitfree then is that to make a waitfree algorithm, you need a thing called a waitfree consensus. This has been talked about by Maurice. And I know of 3 algorithms to achieve waitfree consensus, so let me just name them here. The first one that showed up, no, sorry, not the first one, but one that we've seen is basically a small modification to Lampart's bakery. I'm not going to explain Lampart's bakery. You can look it up yourselves if you've never heard of that. I hope you have. Alex Kogan and Eres Petrank, they took this algorithm, they modified it a bit, and they made a wait-free consensus out of that. And then they used it to make a wait-free queue, because it's simple. Then you have early ice combining consensus dating back to 93, and that is a wait-free consensus by itself. It's actually a universal construction as well. And it's been used by PSIM, which up until recently was the fastest of the universal constructions, and SIMQ, which is the only wait-free queue that actually scales, let's say. So it's the fastest one. So they've used that consensus also to make a wait-free queue. And then there's the third consensus, which we adapted from one of our mutual exclusion algorithms. And we use that to make a wait-free queue. So everybody uses this stuff to make wait-free queues because it's the simplest data structure you can make, let's say. In one file, we used early ice combining consensus. And in case you're wondering why did they use early ice combining consensus if they have their own, the answer is because early ice combining consensus is the fastest, and we wanted to use the fastest, so that's what we used. And also, his is the only one that can aggregate multiple operations in a single step and execute them all, while the other 2 consensus cannot do this. The other 2 consensus, they just decide which thread goes next. We're talking about wait-free, but then, you know, does it really scale? You know, in the end, why do we care about all of that? Well, we care about the tail latency. If you care about tail latency, you care about wait freedom, but well, it would be good if it actually scales. So scaling is easy if you're only reading. So yeah, it's cheating. And there are many generic techniques for reading when you just care about read-only. There are some 2 Readerwriter locks which are really great, and I recommend if you ever need a Readerwriter lock that scales. There are references in the end, they're made by the Oracle guys. There are universal constructions like left, right, and CX. They scale really well, even when there are writes, so because it's wait-free for reads. Then there are the STMs, and now these STMs are also blocking, but they still scale well for reads, and one file is not blocking, and it scales as well. Then there are other not very generic techniques like RCU and RLU. I'm not going to go into that, that's a bit trickier. So here's just a comparison table of the different algorithms. And as you can see, all of them pretty much scale really well if you're just reading. I mean, this is a a red-black tree with 1 million keys, and all you're doing is just lookups. So yeah, you have 36 cores, or whatever Amazon calls that, and you go up to 32 for sure, and it's scaling, and it's pretty much linear. No problem there. What if you're writing? What if you're only writing? You're just doing mutations. Well, let's imagine something which is DAP, which is an array of integers with 1 million integers, and now you're randomly swapping integers, 8 random swaps at a time per transaction, let's say, and that's pretty much disjoint, let's say, so it should scale, but it ends up not scaling. So let's take a look of why that happens. The blue line is a reader. Oops, sorry, that's not the one. Oh, nope. So the blue line here is a Readerwriter lock. And what this means is that if you protect that sequential code with a Readerwriter lock, then you get 90 million operations per second with just one thread. And if you do it with an STM, like TL2, well, you just get 20. So that's like a 400% difference. And yes, the lock has negative scalability, and it takes like 4 cores at least to go up just to the same thing. So that means you need 4 cores all hammering on this data structure or whatever this thing is, and just to recoup the same kind of throughput. That's like, is it really worth to use STM? And if we look at more threads, that was zoomed in close to the 0. If you look at more threads, okay, as you increase the number of threads, you can scale up a little bit more, but I mean, who really has 32 cores and is willing to waste them just to get, a little bit extra performance? Maybe that's not so obvious. So there's a good news, but I'm going to keep that in mind. And before we talk about what the good news is, let's talk about durability. Now, durability is the D in ACID. Or sometimes people call it persistence, or even failure resilience is directly related to this, but I'm going to call it durability for this talk. And what it means is we're going to look at it. So in databases, there's also the concept of consistency, just like we saw in the beginning about linearizability and relaxed. There's kind of the same ideas here. But in databases, you can have a knob that you turn on and you choose what kind of consistency you want for your application. And most databases, they don't have the strongest kind of consistency, which is called serializable isolation. So that would be like the ACID, the full ACID, or whatever. Oops, sorry, the full ACID. Oops, no, wrong. So there are a few which by default have serializability, but it's not common. And some of them, even with the maximum turned on, they still don't give serializable isolation. So it's not that one is wrong or right, it's just that what do the users want? Now for databases, like I said, they can twist the knob and choose whatever they want. But for a data structure, we can't afford to really do that. So I would argue that we have to give from the start the strongest possible consistency. So if we want a data structure that is durable as well as concurrent, we need to give it the strongest kind of consistency in durability and linearizability. And it turns out that the strongest kind of consistency, at least from what I've seen so far, is called durable linearizability, and it was introduced by Joe Israelitz, Amurabi Bendis, and Michael Scott. And this paper is really awesome. I recommend you read that if you ever care about persistent memory. And roughly speaking, what this concept says is that you cannot make an operation visible to another thread unless you can guarantee that that operation has become durable. Whatever the side effects of that operation that can be observed, they are also durable. They exist and are persistent. So let's see an example of something that is not durable linearizable. We have 2 threads. One of them is just trying to set a variable x to 1, and the other one if it sees that x equals 1, it's going to set y to 1. So basically what this means is that y should not be 1 unless x is also 1. And in shared memory, they start as 0, and in durable media, they also start as 0. So thread 0 goes there and changes x, and then thread 1 sees that x is 1 and changes y to 1. And the next step is, for some reason, thread 1 goes before and makes the data durable. So now what we have is a case which shouldn't happen is, well, it was okay for shared memory, but once we made it durable, now this doesn't play well anymore. Now you have corrupted data or inconsistent one. So so far there's been like a distinction in things that give durability, like a file system, and things that give just a concurrency, like an STM. If you use PMDK, which is the new library for people working in persistent memory, there's even a thing called libpmem object, which is a library that just gives durable transactions. So one of them gives concurrent transactions, and the other one gives durable transactions. So one gives the ASCII, and the other one gives the D plus something else of the ASCII, but not completely. And when you combine these two concepts, you get ACID, you get the true ACID, and especially if you can do it with durable linearizability, then you get something that is true ACID. It's what the database gives in its strongest setting. And when I talk about durable media, there are at least 3 big classifications, and there are numbers here, but these are just rough ideas, so don't take them literally. Persistent memory is something whose latency, let's say, goes around 300 nanoseconds, and disk storage, and then you even have network replication. Now, all of these can be seen as durable media. And the thing that's important about when you think about durable media is that in order to guarantee that the data you're putting there is now persisted, you typically need some kind of message or fence or something that takes a round trip to go there and back to say, yes, your data is now durable, you can proceed. So let's say the user wants to write some things. It writes modifications to variable x and y and z into the durable media, and then it asks the durable media, hey, is my data durable? So it takes a while for that message to go and return. Now, it's obvious when you think about networking. Maybe it's not so obvious when you think about persistent memory, but it's also there. It's hidden inside the synchronization fences. So if we think about what this means, it means that you can reason about in a pretty much theoretical way that you can invert the number for the latency, and you get the maximum theoretical amount of operations that are durable linearizable or durable that you can do on a certain media. So that would be like 3 million transactions per second per core on persistent memory, or 10,000 transactions per second on a disk, or 100 transactions on network. But all of this, of course, depends on not just these numbers, it depends on other stuff, but this gives you like an idea of how far you can go and what are the differences. Again, this is the main reason why databases by default do not give the strongest possible consistency, because if you want to give very strong consistency over network, it's very costly. You can only do a few transactions per second, or depends on how fast your network is, of course. So it becomes very costly to do that, so a lot of databases don't do it by default. It's only if the user really needs it, which makes total sense. So what about persistent memory? Everybody's hyped about Optin DC persistent memory. Now persistent memory has existed for actually a long time, several years, but it's in the form of battery-backed DIMM. So it really is a DIMM with a little bit of flash in it, and a battery. So when you put this DIMM and the power goes out, the battery feeds the RAM so that it can be copied into the flash drive, and when it boots back up, it goes back into the RAM and you get the data persisted. But last month we got finally the Optin persistent memory, which does no such thing, doesn't need battery. And it does about 3 terabytes per CPU socket. So you can have 3 terabytes per CPU socket if you can afford it, of course. So, but 3 terabytes is really a large, already a substantial amount. And how do you use persistent memory? Well, again, the paper by Israelitz, Mendes, and Scott describes what are the fences that you need to do. I'm going to skip a bit that. And just so you see the similarities between persistent memory and block storage, when you want to do failure resilience on block storage, so that means when you want to implement a file system or implement a database, you typically use one of these techniques, undo log, redo log, or copy and write. And for persistent memory, it's the same thing. You use the same techniques because it's all about failure resilience. And on disk, you use fsync and fdatasync to order the writes to the device so that this algorithm is going to work correctly. On persistent memory, there's different instructions to do that, but they have the same purpose. And to guarantee that the data is durable, remember this round trip to the device, it's again fsync, fdatasync, and on persistent memory, it's psync. Now, I would argue that one of the hardest things in databases and file systems is to design a correct recovery mechanism. So is to use those techniques, undo log, redo log, whatever they are, to make correct thing. And the reason is the power cut can exist anywhere, can occur anywhere in the code, right? So you don't know where in the execution that's going to happen. And the recovery has to be correct, otherwise you're going to corrupt your data. You're going to corrupt your database. And if anybody has ever used the database and had this problem, you know, recovering a database can take minutes, hours, days. And with persistent memory, that time is going down. There's some people that say that they can recover the database in seconds. But what if there was a way to not even have a recovery at all, if it was just instantaneously brought up? Well, Lockfree algorithms have this property of null recovery. Now, not all Lockfree algorithms have the property of null recovery, but the majority does. And again, on the paper by Michael Scott, there is this concept of null recovery, which says Lockfree algorithms really don't need it in persistent memory, some of them anyway. And because one file is itself a lock-free algorithm or wait-free, it does have this property. So what this means is that in the event of a failure, the transactions that were being applied will just, you know, just continue applying it, and there's no explicit recovery method needed. It also means that because there is no explicit recovery method, all it does is apply the last transaction if it was ongoing. So recovery takes as much as a transaction takes. So that's less than a microsecond, depending on the size of the transaction, of course. So now let's go back to what we were talking about, scaling for writes. What does that all mean on scaling for writes? So again, in volatile memory, we can scale for writes, but it takes so hard to catch up with what a global lock does that it's kind of hard to justify. But in persistent memory, we can't just use a lock. Once you decide that you need persistent memory, you need a technique to protect your data from failures. And that means you need an undo log, redo log, copy and write, some kind of technique that protects it. And just the fact that you're adding this technique to your data structure, to your data code, it means that you're going to have less throughput. So an STM, or a persistent transactional memory, better said, can use the same logging technique, can use the same, not just for the concurrency, but also for the persistence. So what this means is that now the difference is no longer 400%, it's 40% in this specific case, and this can be even improved a lot. And it also means that once you go to 2 threads, you're already ahead of the game. You've beaten the global lock, plus whatever technique you use. So that's like the real insight. Once you go into persistent memory, you can scale, and you can scale very high for writes. This is just doing writes. Again, as long as the workload is disjoint access parallel. If the workload is not disjoint, then you cannot scale. And I would argue that's even impossible. So I still have a few minutes. The future, but let's start the future with what we can do today. And what we can do today is STMs are already existing for many years, and they're a nice way to abstract so you don't have to worry about locks, but that's, I would argue that's pretty much it, but it's still very useful. But now with persistent memory, this can change because, yes, you can use persistent memory just as if it was a disk, but if you use it with load and stores, it's going to be way faster because you don't have to go through the entire virtual file system stack and all that stuff. And because transactional memory was originally intended as a way to make lock-free data structures, sorry, I'm skipping. It's kind of natural for them to be used then to make an STM that does the lock-free data structures, and on top of that, gives ACID transactions. So you get the concurrency and the durability in a single transaction. And it also means we can make weight-free databases. So for the first time ever, I think, we can make a database that does not have locks. Let me say that again. We can make a database without any locks, okay? So that's pretty cool. So the near future is, you know, like everywhere in engineering, you have to make some trade-offs. So you can think of this as, you know, a universal construction or something like one file. Yes, it's generic, and yes, it's weight-free, but it doesn't do disjoint writes. And then you have the blocking STMs. Yes, they're generic, and they do disjoint writes, but they're not weight-free. So they scale for writes, but they're not weight-free. And then you have the handmade lock-free data structures, which are not generic and not easy to modify. Some of them scale for writes. What if you could have all of it together? Well, if you could have all of it together, it would be something I would call the holy grail of concurrent data structures. And notice I wrote the holy grail of concurrent data structures, not the holy grail of concurrency. That would be a much, much trickier problem and likely even impossible. So I don't believe there is a holy grail for concurrency, but I do believe and pretty certain that there is a holy grail of concurrent data structures, and it's very close. And I don't even care who gets there first. I just want to use it. So that's really, really what it is about. And of course, it's going to have to scale for reads, and it's going to have to do weight-free memory reclamation and all this stuff because one file already does it. So just copy the code and put a different algorithm on top of it. Now the thing is, yeah, okay. So I still have a few minutes. Now, yeah, there's one thing I want to talk as well about this, is that this thing that will be made, hopefully soon by someone, it doesn't have to really be as good as what it already exists today. It doesn't have to scale as much as TL2 or P or whatever, all these things. It just has to be good enough, scale enough, well, weight-free is 0 or 1, so it has to be weight-free, but you know, it doesn't have to be all that the others, it doesn't have to beat the others, it just has to be good enough. And because it does all three things, it becomes way, way interesting. Now, in the not so distant future, so after this, once we have something that is weight-free and durable linearizable and does transactions, can we use it to make a database? And what does that look like? Well, because all the code that we write inside the PTM, protected by the PTM, is sequential, what this means is that if you use it to write a database engine, to write the database, all the code is going to be sequential. So it's very easy to read, it's very easy to maintain, because all the hard parts, which are the concurrency and the durability, are taken over by the PTM. This is the work of the PTM. And there's no need to write a recovery operation because the PTM takes care of that. In fact, even the PTM itself doesn't need a recovery because it's locked. And the really big insight is that because you have these transactions, you can have it inside your database engine, you can have a transaction that touches the tables of the database, any metadata, the indexing data structure, and the records, all in the same transaction. All looks like sequential code. And it's going to hopefully scale, and it's going to be correct, failure resilient. And because it's weight-free, it will be good in low latency, it will have low latency at the tail, and it doesn't have any locks. So it really is a new concurrency control in that sense. Concurrency control that takes advantage of double word counts, but it is. And do we even need DBMSs anymore? Do we even need databases? And of course we do. We still know this is just a niche application where then the developer, if it's simple enough code and he's confident enough using this tool, he can directly do the transactions himself and not have to go through the key value store. So the store, through the transactions, becomes embedded into the application code. You're really writing the code as a developer. You don't need to do the get and the put of the key. So what did we learn today? Well, Lockfree is mostly about progress. Waitfree is mostly about tail latency. Again, these are kind of opinative, but neither are really about throughput, typically. And to do a wait-free algorithm, you need a wait-free consensus. And scaling for reads is easy. Scaling for disjoint access parallel writes is hard. And scaling for non-disjoint access parallel writes is probably impossible, but that's my conjecture. You can use a Weightfree STM or a Weightfree universal construction to transform a sequential data structure into a weight-free data structure, and you won't have to do a lot of work or very little one. So that's it. That's all. I think we still have a couple minutes for questions.
Yes, Pedro, thank you. So guys, we have minutes for one question. If anybody have questions. No questions? That's interesting. Oh.
Thanks for the talk. Could you please shed the light? How did you test the one file library? Was it just mathematical reasoning or it was some kind of framework? I don't know what.
Okay, so you care about the STM itself, right? The correctness of the STM.
No, I meant the library that was recently implemented, one file.
So that's an STM. That's a software transactional memory, yes. So we did a lot of testing, like unit testing, concurrent testing. The way we do that is the secret sauce. So we spent more time doing tests than actually the implementation, which is normal in a software engineering project, I would say. And the way we do that most of the times is we take a sequential data structure like a queue, we wrap it in the STM, and then we test all the invariants of the queue in a concurrent setting. So we have really hard stress tests that test whether a queue is linearizable or not by checking multiple invariants. We did this for queues, for sets of different sizes, a lot of different testing. So that's like the experimental part. So of course, that doesn't cover all the cases, but it does give you a really good confidence. Yeah, because like pretty much any STM that we've tested did not pass those tests, other STMs. But that's biased because we fixed the hours until it passed our tests, because that's what tests are for, right? So all the issues that we found with our tests were fixed in the STM. So that's one part. And we did make some formal proof, but again, proofs can have errors. So we made formal proof for the STM as well, for the algorithm. And that's it. That's about as much as you can do, because one thing we looked at was using things like spin or JSF or something like that, which proves all possible interleavings, the correctness of all possible interleavings. And the problem with that is that, first, it only works for very simple algorithms. So putting an entire STM code might not really work. And then it only works for like 4, 5, maybe 6 threads. So if you ever want to use more than that, you no longer have the proof that it works. Because when you have a lot of threads, basically what happens in these tools is you have state explosion. Because computing all the possible interleavings of all the instructions is pretty much exponential. So that's what happens.